Hi all, we are discussing about instruction set architecture. So it is very important to know the concept of instruction set architecture, and we have seen some characteristics of the instruction set architecture. So we have also seen some examples of the instruction architecture and what are the important blocks. It is very important to understand this the active necessary blocks of the instruction set architecture. Here we have arithmetic and logical unit, ALU. ALU stands for arithmetic and logical unit. This ALU is responsible for doing arithmetic operations, and here we have a set of registers. See, here we have 8 registers, and these 8 registers can be selected with 3 inputs ABC, and this will select any one of the register, which is called 3 by 8 decoder. The 3 by 8 decoder 3 by 8 decoder is used for selection of a register, for selection of a register. So the specialty of this 3 by 8 decoder is that it takes 3 inputs and any one of the output is on. This is called 3 by 8 decoder, and such output will go to one multiplexer. Specialty of the multiplexer is that it takes multiple outputs, multiple inputs and single output. So the multiplexer is used here, which takes multiple inputs and single output, multiple inputs and single output. So this is about multiplexer. So ultimately ALU receives the value from any one of the registers, and from this multiplexer 1 and from this multiplexer 2 it receives another register value, and it performs ALU performs arithmetic and operation. Which register has to be selected is decided by the control unit, and what operation is to be performed decided by instruction decoder. So the content of the instruction decoder is sent to our ALU. Then ALU decides what operations it required to perform. Then control unit sends what are the registers which contains the operands for this operation. These are the important blocks of microcontroller. So the digital modules are best described by registers they contain. Remember, registers means they can be IR register, PC register, stack pointer register, MAR register, MDR register, IR, PC, stack point, MAR, MDR register, and any type of other registers they say. And next we see that micro operations performed on the data. We have seen that the micro operations are the smallest operations performed on data stored on these registers. Elementary operations done on data in the register. Those are called register transfer language, register transfer language, concise symbolic expressions like add and load. So add and load are register transfer elementary operations. How to describe a computer means using set of registers and their function, sequence of micro operations, controls that initiates and maintains, sequence of micro operation. What are the controls means? What are the control signals? Today, from a programming point of view, assembly is the lowest level we use to define these registers, instructions, and their order of execution. So these registers, instructions, and their order of execution. So registers and instructions are order of their execution. Programming in assembly. To program in assembly, we need knowledge about hardware design. We need to have, someone should have the knowledge about hardware, how hardware is designed, what are the available registers, what are the different kinds of memory addressing. And memory addressing means it's very important to understand how operands are fetched from memory. How operands are fetched from the memory is called memory addressing. And next is IO. IO stands for input and output. IO stands for input and output. So knowledge about instruction set. And what is the knowledge about? You should have what are the instruction set. Next, what type of memory located inside CPU? So registers means it's a type of memory located inside the CPU. Remember, register means temporarily located, temporarily stored, or you can call it as buffer. So how do you define a register? Register is nothing but a temporary storage area which can hold some data temporarily, can hold a single piece of data. So what is meant by a single piece of the data? It can be 32-bit data, 16-bit data, or 64-bit data. It depends upon length of the bits, length of the register. So length of the register means length of register means number of bits in the register, whether they may be 32-bit or 64-bit. useful in both data processing and control functionalities. So these registers are used both in data processing and also for controls and functionalities, like PC holds the address of the next instruction, so it comes under controlling the functionalities. Like MAR contains some address that has to be fetched from the memory. These are called the registers used for control functions. So there are some special purpose registers such as program counter, instruction register, accumulator or working register, flag register. So when I say register, register can be, there are some special type of registers such as PC. PC stands for program counter. The specialty of this PC register is that this PC register is used to store address of the next instruction to be executed. So this register is used to program counter register is used to store address of next instruction to be executed. Next, we see that instruction register, that is IR. So IR stands for instruction register. IR stores the current instruction to be executed. So the IR instruction register contains the current address, the current instruction to be executed. Next I have accumulator or working register. So I have accumulator. So what is this accumulator? So the accumulator is a special type of register. Some CPUs are accumulator based CPU. That means when ALU performs, ALU means arithmetic and logical unit, takes the input from one of the register, and one of that register can be AC and BR. This AC, what happens, this is called ALU. AC is called accumulator register. The specialty of this register is that when, let's assume A is 10, B is equals to 20, then this A plus B becomes 30. So AC register contains, let's assume 10, BR register contains 20, ALU performs 10 plus 20, again the result is stored in 30 in accumulator register. So this for that reason accumulator is called a special type of register. Why? Because it is used to store the the result of an arithmetic operation. So you should understand that ALU is used result of any arithmetic operation. So it is used to store the result of any arithmetic operation. Which one? This accumulator or working register. Next we have some flag registers. Next I have flag registers or status registers. So the speciality of this flag registers or status register is that they store, flag means it can be 1-bit register. For example, there is a flag called carry flag. Carry flag means while performing any addition or subtraction, or especially addition, you may get carry. You may get, then this carry is set to 1 in case of this register. So this is called carry flag register. So like that, these are some special purpose registers, and there are also some other register which I want to mention is general purpose register. They are general purpose register. In short, I can call it as GPR. So these GPRs are general purpose registers. They don't have any special name. They don't have any special name, but they can be used for general purpose. Like they can be referred as ABC or R1, R2, R3. So these are called general purpose registers. Next we see the format of assembly statement. Just remember, assembly means it is just above machine level language. Machine level language means 0101. This is the instruction format which user can't understand. So assembly language instruction means they will use some codes. These codes are called mnemonics. These codes are called mnemonics. Example for assembly language instruction mnemonics is like add, load, store, something like that. These are called mnemonics. So we will see a label, we'll see the format. First we try to understand this one. This is opcode, or it is called operation code. opcode or operation code. What instructions to be carried out by CPU? Only valid instructions are ALU. So this opcode is exactly useful for ALU. First, this opcode will be decoded by instruction decoder. Decoded by instruction decoder. Then this is go as a input to ALU. This goes as a input to ALU. Next, we have the operands. These are called operands. So the operands are nothing but, I tell you, operands can be registers, general purpose registers, or they can be some values in the instruction itself, or they can be address of memory location. So this is called operands. These are called opcode. Next example is opcode is add. Example for operands is this one. Next we have a comment section. Explanatory text, optional but very useful as assembly programs are hard to understand. So what this do, you are giving the input as RC, RA, RB. These are the operands. So here what happens, here in the comment section, this is called comment. It is useful only by the user, not by the program. Here it is mentioned that the content of RA and RB added and result is stored in RC. So that is the specialty for that reason. So RC, first register stores the result, second register is the first operand, third register is the third operand. So what happens here, the content of RA and RB is added to the content of RA and RB is added and stored in RC. So this is about the content of RA and RB is added and stored in RC. So if I give the order like RA, RB, RC, the content of RB and RC is added and result is stored in result is stored in RA. So this is about format of assembly statement. But one thing we missed is that is the label. This is called label. What is an identifier? This is also called identifier. So what is this identifier and label? Labeling code are to indicate a program destination address for jumps. as in this is a label, means this is like a number, unique number given to this instruction. Here example is L20. Where it is useful means, for example, if I have L21, if RC is less than 0, go to L20. So here L20 means it will again go back to the statement. So the L20 is used, labels or identifiers are used to label the instruction. It's a unique identifier for the instruction. Next we see the example of an instruction set. We will use instruction set from some processor called PIC16F87 for our discussion. So some other textbooks refer MIPS or x86. They are still too complex to start with. When you are more familiar, you can learn use any of the instruction set. For time being, we will use instruction. We'll try to, for the sake of understanding easily, we will take an example of instruction set PIC 16F87. So this is called PIC 16F87X. So there is also an instruction, processor instruction called MIPS or x86. So these are the examples of the instruction which are categorized. We will see example. First we will see the notation. F stands for file register, and next B stands for bit. Next W stands for working register. Next L stands for literal. Literal means it is a constant. Remember, literal means any constant value like 10, 20, 30. Next Z. Z stands for conditional execution. So Z stands for conditional execution. So this conditional execution, Z stands for conditional execution, like if, go to, if else, like that. Next I have small d, which is referred to destination. Small d stands for destination bit. So small d stands for destination bit. Destination bit can take the value 0 or 1. So the destination bit can take value 0 or 1. If it is 0, store in working register. So small d can take two values, 0 or 1. 0 means store in W. W stands for working register. So D stands for 0. If D means 0, store the result in working register. If D is equals to 1, so if small d is equals to 1, then store in F. Store in F. F stands for file register. F stands for file register. W stands for working register. So D is a destination bit. If it is set to 0, the result is stored in W, working register. If D is set to 1, the result is stored in file register. Next, we use WRF instead. So these are the examples of the instruction set architecture for PCI processor. Now we see how it is formatted. We see the opcode field description. We'll try to understand the instructions. Opcode field determines the instruction. So here opcode determines the instruction. For example, the opcode field description has been given here, which is easy to understand. So registers, what type of instruction, what are the registers it contains, what bits, any literals, depends upon opcode, all these things. We'll see what type of instructions determines the instruction type. Now we understand that this type of instructions are very useful, and the opcode field description, you might have seen, in place of opcode, F stands for register file address. F stands for register file address. F stands for register file address. And what is this register file address? F stands for register file address. So next I have W. W stands for working register. So F stands for F stands for register file address. W stands for working register. Next I have small b. Small b stands for bit address. Small b stands for bit address with an 8-bit file register. With 8-bit file register. So it is an example of a 8-bit file register. Next I have small k, it's a literal field. Small k is a literal field. Small k stands for literal field. What is the specialty of this literal field is that literal field is used to represent some constants. Next I have small x, don't care location. The assembler will generate code with x is equals to 0. It is recommended form of use for compatibility with the microchip and software. Now we have small x whose value can be 0 or 1. So small x can take value 0 or 1. So what is the specialty means? This value can be 0 or 1. This 0 means it is recommended when x value is 0, then it is recommended form of use for compatibility with microchip software tools. With microchip software tools. It is a microchip software tools. So it is a one type of the flag bit register. It is one type of flag bit register whose content can be specified by a don't care location concept. Next, I have small d. Small d again can take, see small d, small x, these are flag registers. These are called flag registers. And the specialty of them is that the specialty of them is that they can have only two values, either 0 or 1. So they can take only one value, either 0 or 1. So the 0 indicates that store result in W. W stands for working register. So W stands for working register. So if small d value is equals 0, then it indicates that it is a result can be stored in working registers. Or if small d is equals to 1, then you can say store result in F. F stands for file register, which is called file register. So store the result in F or store the result in W. Store the result in F means file register, If D is equals to 1, store the result in file register. If D is equals to 0, store the result in W. W stands for working register. Then I have PC stands for program counter. All of you know that program counter register is used to store the address of next instruction to be executed. Next I have TO. TO stands for time out bit. TO stands for timeout bit. So what is this timeout bit? That means if a processor is waiting for some IO operation and if it couldn't complete within specified amount of time, then you can call it as timeout bit. Next I have PD. PD stands for power down bit. PD stands for power down bit. The specialty of this power down bit is that when you set power down bit PD to 1, then power is off. When PD is equals to 0, power down is on.